Hello everyone, my name is Mohammed Nabeel. It's a great pleasure to talk about our work on CoFHEE, a coprocessor for fully homomorphic encryption execution. I would like to acknowledge my co-authors from NYU Abu Dhabi, NYU New York, and Khalifa University Abu Dhabi. These days, many entities depend upon cloud service providers for their data processing needs. With the current deployed crypto systems, best security that can be achieved is the data can be in encrypted format while in transit and at the storage. But it must be decrypted so that the server can perform computation on it. What it means is if there is any security compromise happening on the server side, the attacker can get access to the raw user data. Fully homomorphic encryption or FHE is a cryptographic scheme that enables computation over encrypted data. With FHE, the client can encrypt the data using a secret key before sending it to the cloud, and the cloud service provider can perform computation on encrypted data, and the encrypted result is returned to the client. Then the client decrypts with the same secret key used for encryption. As the data stays encrypted throughout the computation, even if any security compromise happens on the cloud side, it will not leak the user's raw data to the attacker. To understand why FHE is not widely deployed, though it has the potential to provide strong security and privacy guarantees, let's take a look into the FHE ciphertext. Most of the FHE schemes are based on the ring learning with error or RLWE. In RLWE, ciphertexts are over the negacyclic ring and the ciphertexts are represented by a pair of polynomials. As it's a ring, the underlying operation is modular arithmetic. For FHE, depending on the application and the target security level, the polynomial degree can go up to 32,000 and the coefficient modulus can be as large as 1600 bits. What does it mean is the ciphertext can have a size as large as 25 megabytes. Because of the huge polynomial size and as the fundamental operation is modular arithmetic, software implementation on modern processors are 6 orders of magnitude slower when compared to doing the same workload on unencrypted data. Here is where a dedicated hardware that is custom built to perform FHE specific computation can help, and that is the motivation for CoFHEE. Among all the polynomial operations, the most complex one is polynomial multiplication. Naive implementation of polynomial multiplication has a time complexity of big O of n square. But if we can transform the coefficient representation of the polynomial to its point representation, multiplication can be done with the time complexity of big O of n. This transformation can be achieved using a technique called number theoretic transform or NTT. NTT is discrete Fourier transform over a quotient ring and can be implemented using the FFT algorithm with a time complexity of big O of n log n. So the overall polynomial multiplication has the same time complexity of big O of n log n. This is absolutely critical as a polynomial often has 16,000 to 32,000 coefficients. CoFHEE focuses on accelerating polynomial operations as it is the basis of all high-level FHE primitives. Along with entity, these are the other lower-level operations that is accelerated in CoFHEE. There is C-mod mul, where a constant is multiplied with a polynomial. Then there is P-mod mul, where point-wise multiplication of two polynomial is done. P-mod add, point-wise addition of two polynomial. P-mod sub, point-wise subtraction of two polynomials. As our main goal is to fabricate an ASIC, we had some design constraints. The target technology is 55 nanometer with global foundry, and overall design should fit in 12 millimeter square of chip area. And to run a CryptoNet workload on CoFHEE, polynomial degree chosen is 8192 and coefficient modulus chosen as 128 bit. This gives a memory requirement of around 896 kilobytes, which is close to 1 megabyte. And in Global Foundry 55 nanometer technology, this much memory takes around 9 millimeter square of chip area. That leaves only enough space to fit one 128-bit modular multiplier. So our goal is to achieve theoretical minimum cycle count for all the polynomial operations that is possible to achieve with only one multiplier. There are mainly three design blocks in CoFHEE. A processing element that performs modular arithmetic by taking two operands as input, and it also performs radix to butterfly operation that is required for NTT. Then there is a memory pool to store the polynomials and the intermediate results, and a controller to generate address and to load the operands from memory to the PE and to store the result from PE back to the memory. Communication between the controller and the memories happen through the ASIC interconnect. The controller has 5 ports to the ASIC bus, and all the 5 will be completely utilized while performing NTT, where in the same cycle, 2 operands and the corresponding triple factor will be loaded to the butterfly unit from the memory, and previously computed results have to be stored back to the memory. To reduce routing complexity to the memory for NTT, dual port SRAMs are used, with which it is easy to load or store 2 values at the same time. Then there is a command FIFO to sequence the polynomial operations that need to be performed. Then there is an SPI and an UART for communication with the external host. The external host can load the data and the record instructions through this interface to the CoFHEE. There is another UART interface to communicate to the host when the execution is done, along with the start address of where the result is lying. Then there is a DMA to move the data from memory to another. Then there is also a ARM Cortex M0 as a control processor. And there is a general purpose configuration register space to program polynomial parameters like polynomial degree and the coefficient modulus. And also it contains all the control registers required for other design elements like PLL, chip IOs and all. CoFHEE can be either used as an off-chip accelerator or it can be integrated in a bigger SoC on-chip. In both the cases, one can connect multiple CoFHEE instances for parallel operation. Except for Cortex M0, which we got as an IP from ARM, all other design blocks are coded in Verilog. After integration of these design blocks, CoFHEE is verified through RTL simulation. We made use of SymPy library in Python to generate test vectors for NTT. We also prototyped the design on FPGA, but with polynomial degree of 4000. We also wrote a Python API to communicate with the CoFHEE from external host. Then the design is taken through backend implementation using industry standard design flow using EDA tools from Synopsys and Cadence. Here is the implementation result of CoFHEE. The frequency achieved is 250 MHz and it is mainly decided by the memory read latency, which itself is around 4 nanoseconds. As can be seen from the floor plan diagram, it's a memory dominated design and memory takes around 83% of the design area and PE takes close to 6.5% of the area. Here is the post-silicon validation result. We are able to perform 8K NTT in 53,535 clock cycle compared to the theoretical minimum possible with only one multiplier in the design, which is 53,240 clock cycle. The extra cycle loss is mainly because of pipeline flush delay after each stage of NTT. We are also able to measure accurate power numbers during computation. With simulation, it would have been extremely difficult to calculate the actual power numbers. While performing NTT, we note that the average power consumed is 24.4 milliwatt and peak power consumed is around 29.7 milliwatt. As CoFHEE is targeted for ASIC fabrication and had an area constraint of 12 millimeter square, for a fair comparison, we compared the performance achieved per millimeter square for NTT after applying the scaling factor to match the technology of the related work. And we see that the CoFHEE is slightly better in this metric when compared to F1, which is an ASIC accelerator for FHE with post-synthesis area of 150 millimeter square. Besides ASIC, there are a number of works that propose FPGA-based solutions, but as we cannot map FPGA resources to silicon area, the performance per millimeter square metric cannot be accurately calculated. To conclude, CoFHEE is the first silicon-proven ASIC implementation for FHE computation, and with that we are able to measure the power numbers accurately. Performance per millimeter square for NTT metric shows CoFHEE is slightly better than the related work. As CoFHEE supports polynomial operations over ring, CoFHEE can also be used for any RLWE-based schemes. Thank you for listening, and if you are interested in learning more about CoFHEE, please read our paper.